Right, first thing we want to cover when it comes to the particle model is this idea of density. So rho equals mass over volume, or density. Sometimes we write it as rho. It looks like a P, but it's actually a Greek letter called rho. And the density is in kilograms per meters cubed. And so you can basically guess this is meters cubed, this is kilograms. What the density does, it basically tells you how much mass you can fit in a certain volume. Now, one thing you do need to know about is the idea of solids, liquids, and gases, and how do they relate to density. Or basically, your solids are going to be super dense, really high rho, and your gases are going to be really not very dense, okay, so really low density, and your liquids in the middle will basically be about a medium density, okay. So you should also be able to draw those all out, and the idea is your solids are going to be really close together, your liquids are going to be close together but a little bit more space in between them, and your gases basically are going to be really far apart. They've got loads of energy, they're moving around in places, and your gases, they actually fill up the container, okay, whatever container they're in, they fill it up. And that's why the density is quite low, because they're basically all spread out throughout this container. So one other thing is that, well, hopefully you should know that you can get changes of state. So you could go from a solid to a liquid to a gas, okay? So you can go from one to the other and back again, and you can even sometimes skip. You can go straight from a solid to a gas, for example, or something like that. And the idea is that all of these transfers are reversible, and they're also what we call physical reactions. They're not chemical reactions, and the reason why we can say they're not chemical reactions and that they're physical and reversible is that when you reverse them, the material retains its original properties. So for example, when you go from ice to water, if you then decide you want to freeze it again, the ice that you get back when you freeze it will be exactly the same kind of properties as the ice that you had when you first melted it, okay. So that's basically it. Another thing we need to talk about when it comes to these particles is that these particles have something called internal energy. And the idea is you might have an object over here like this ball, and if the ball is not moving, we might say, well, this ball doesn't have any energy itself, right? But actually inside of the ball, remember, it's made up of loads of these particles. That's the whole idea of this particle model. So these can have some energy themselves, and the energy these particles have will either be kinetic energy or it will be potential energy. Okay, so there's two options. And if you were to sum those two up, that's what you'd call the internal energy, okay? When you add those two together. And what we do know about the internal energy is if you increase the temperature of the particles or the ball, then basically the internal energy will also increase. And that is because you basically increase the kinetic energy when you add your heat energy there. And basically when you heat something up and you add heat energy, it can either lead to a rise in the temperature, like we said over here, or what can happen is instead, if you're given this heat energy and the temperature doesn't rise, what could happen is you're actually increasing the internal energy instead. So it would mainly be the potential energy that you're increasing instead of the kinetic energy, okay? And that is exactly what happens when you get a change of state, like we saw before, solids going to liquids, liquids going to gases. You might heat up the solid to cause it to melt into a liquid, and when you do that, the heat energy, instead of going to increases in the temperature of the solid, will actually cause it to change state. Now we can also look at temperature change and specific heat capacity, just like we did earlier on when we looked at the temperature section. So we're going to use the same formula, E equals mc delta theta. I won't go over it again since we've already gone over it, but essentially this will tell us all about how much energy to transfer to get a certain temperature change or something like that. Whenever you have any three of these, you can work out the fourth one. And so just remember, specific heat capacity is going to be different between different materials, and it tells you how much energy you need to input to actually get the temperature to change. Okay, so how hard is it to get that material to change temperature? Well, just like we said before, we also get times where we have heat energy and we don't get a temperature change. So what's going on there is you're changing state. And so instead of using this formula here where we've got a temperature change, we have no temperature change. So instead we use this formula, E equals ml, and so this is all to do with specific latent heat. And latent heat is basically where you apply heat, but you don't cause a temperature change, you cause a change of state instead. So the energy over here will be equal to the mass multiplied by the specific latent heat. So just like specific heat capacity, it's a quality of the material. So for example, water would have its own specific latent heat, and depending on how much mass you've got, this equation will tell you how much energy is needed to change the state of that material, okay? And so it is important to note as well, you've got two types of latent heat. So you've got the latent heat of fusion, and this is basically when you go from a solid to a liquid, and you also have the latent heat of vaporization, and this is when you go from a liquid to a gas or a vapor, okay? So there's two types of latent heat that you do need to be aware of. What would that look like on a temperature curve? Well, if you were to put a temperature on the y-axis and time on the x-axis, and let's say we're heating something up this whole time, what you might see is initially you add heat and you see the temperature rise as you might expect. Then you get to this point where you get a change in state. At that point, the temperature isn't rising anymore. The heat energy you're inputting is being inputted to the internal energy of the material instead. And so you don't get a change in temperature, you get a change in state. That's where your latent heat is kicking in. And then after that, you might heat it up some more, and then it might change state again over here. So you might go from solid to liquid to gas, for example. Okay, and these flat sections is basically where you have your latent heat going on. Basically, you're adding heat, but the temperature is not increasing. Instead, it's going to actually change the state. So if we go back up, we also looked at gas particles. And so now let's actually zoom in on this and look at this in a bit more detail. So when you have these gas particles in a container, so we'll draw a container for them, these particles are moving randomly in all directions, okay? And what happens is they actually collide with the walls of their container. And when they have these collisions, this is what causes what we call pressure. And what we can say is the higher the kinetic energy, or the average kinetic energy of the gas particles, then the higher pressure you're going to get. And actually we can even say that these are directly proportional to each other. So these have a directly proportional relationship. If you double the amount of kinetic energy that these gas particles have, you will also double the pressure. And so over here, this container has a fixed volume. So what happens is if you keep the volume constant and you increase the temperature, you will also end up increasing the pressure, okay? So if you keep the volume constant and you change the temperature, you will change the pressure. And the reason for that is because essentially the temperature gives these particles more kinetic energy. The more kinetic energy they have, the more collisions they're going to have with the walls of the container, the more frequent those collisions are. And the more frequent those collisions are, basically you get higher pressure, because remember, pressure is basically force divided by area. So the more frequent those collisions are, you have a higher average force on your container walls, okay? Just like if we kept the volume constant and we changed the temperature, it would affect the pressure. We can also say the same. So now instead, let's say we keep the temperature constant and we change the volume. So let's say we increase the volume. What that would do, as you might expect, it would actually decrease the pressure. And if instead we were to, again, keep the temperature constant and decrease the volume, what might happen is you'd actually end up with an increase in pressure instead. And it's basically for the same reason. It's all to do with the frequency of the collisions. The smaller that space is, the more frequent collisions you're going to get, okay? One way we can actually define this a little bit better is by using the equation for Boyle's law, where Boyle's law is basically PV equals a constant, okay? And this basically tells you what happens if you keep the temperature the same. So you have the same temperature and you have a constant over here. That means that when you have pressure and volume set to certain values and you change one of pressure or one of volume, they're indirectly proportional. So basically as one increases, the other will decrease, and this will always be a constant at the same temperature, right? So if you have the pressure volume for one occasion and then it tells you, well, we change the pressure to a certain pressure, you can work out what the volume would be, and vice versa, okay? And one other thing to note, we didn't mention it, but pressure, the standard unit is pascals. Okay, and if you're doing separate sciences and you're doing the higher tier, you also need to know about doing work to increase pressure. So one specific example you might have is you might have a container like this, and you have the wall over here, and inside here you got loads of gas particles. And what you might have is something like a pump or a syringe over here, and you might decide you're going to push and do some work on this wall to actually push it over here. So now the new position would look something like this. So again, you'd have your container, but now all of a sudden your wall is over here, and so you've actually decreased the available space and you've decreased the volume over here. So what happens is, as well, is you've done some work because you've applied a force over here to push this syringe in, and it's traveled a certain distance to actually, whatever distance that is, you've moved the wall basically. And so what's happened is you've done some work. And if you've done work, that means you transferred energy. So where did that energy go? Well, the energy actually went to internal energy in the particles, the gas particles inside here. And so as a result, because you've increased the internal energy, you might have increased the kinetic energy of the internal energy, the kinetic energy component, and therefore you've increased the temperature of the gas. And so what you might notice is if you were to hold the sides of this wall, sides of this container, when you start to squeeze it, you will notice it starts to heat up, and that's the reason for that, okay? All right, 3 topics down, we got one more to go, and that is atomic structure. Perfect, so let's get into atomic structure. So very simply, atomic structure, what is the structure of an atom? Well, generally we say it has a nucleus in the middle, and inside of the nucleus, you're going to have these positive protons, and you're also going to have some neutral neutrons, okay? So they don't have a charge, we'll just draw them like that. And then orbiting around our nucleus is going to be these electrons. Yeah, you have these electrons, and they're basically arranged in these shells, okay? So I'll put 2 on that shell, and there might be a few more over here. And the idea is these electrons, they orbit around, but that they're at fixed distances. Okay, so you won't see any electrons over here in the middle. You'll just see them at these fixed distances orbiting in these kind of circles. Okay, so that's one representation of an atom. So another way to represent these is to use symbols. So for example, we could have chlorine, and chlorine has an atomic mass of 35. So that means the total number of protons and neutrons are 35, and it has an atomic number of 17. And that means the total number of protons is 17. And usually, because chlorine as an atom, it would usually have the same number of protons as electrons to make it have zero charge. So you can also say it has 17 electrons, okay? You can also get isotopes. So isotopes is basically where you have something with the same number of protons. So it would also have 17 protons to make it chlorine, but you might have a different number of neutrons, and as a result, your atomic mass would be different. So it might be 37 instead. Okay, so that's an isotope. We do also need to understand how we developed the atomic model that we have today. So this is in the revision guide that I linked below, a nice written example of this. So I'll just basically give you a quick rundown of what we went through. So initially we had this idea of indivisible atoms. So this is just an atom, and we said, well, there's nothing in it, there's nothing contained within it, it's just the smallest piece component that we have that makes up everything else. Then we discovered the electron and also the nucleus, and we came up with the plum pudding model instead. So the plum pudding model is you have this big atom over here, but within the atom you have kind of these negative electrons embedded within it, but the overall charge of the atom is positive, right? So you have this positive ball, and you've got these negatively charged electrons embedded inside of this atom, okay, like a plum pudding. Then we did the alpha scattering experiment, and what we found was we had this piece of gold leaf. We then fired some alpha particles at it, and we would expect the alpha particles to go straight through, but instead what we found was that these were scattered. So we had some angles of deflection, and because of this we realized that actually this doesn't match what we expected from the plum pudding model. So that's when we came up with the nuclear model. So the nuclear model, we basically had this ball of positive charge in the middle, and we have the electrons basically going around on the outside. Okay, that's the whole idea of the nuclear model. And then someone called Niels Bohr came along, and he said, well, these electrons, they don't just orbit around the outside, but they orbit around the outside in these fixed shells. Okay, so he came up with this idea that we have shells and we have fixed energy distances or fixed energy levels that the electrons orbit in. Okay, so you can see basically the way this developed is we did different experiments, we updated our hypothesis, or we made a hypothesis, we updated our models based on the experimental evidence to get the model that we have today. So this was basically later updated when we discovered the neutron and the proton, and we said, oh, well, okay, this nucleus itself is also made up of particles, which some of them are protons and some of them are neutrons. Okay, so that is the atomic model. Some of the most interesting stuff that you get in your paper is to do with nuclear decay. So we'll start off by looking at nuclear radiation or radioactive decay. And so essentially the whole idea of radioactive decay is that sometimes you have atoms which are really unstable. And when you have an unstable atom, it tries to become stable, right? So this unstable atom, it wants to become stable. And so the question is, how does it do this? Well, all it does is basically this unstable atom, it goes and it decays. And when it decays, it can actually start to try to become stable like that. And so the rate of the decay we call the activity, and this is measured in becquerels. Okay, so BQ for short. And so there's a few types of decay that you do need to know. So the first one is alpha particle decay, and this looks very similar to a helium nucleus. So the idea is it's got 4 for the atomic mass and 2 for the atomic number. That means it's made of 2 protons and 2 neutrons. And the way that an alpha particle works is you have your unstable nucleus, and it releases this alpha particle, and as a result it tries to become more stable. So what that might look like in the form of an equation is you might have an atom X with let's say 200 and 100 for the mass and the atomic number, and this decays and it produces therefore this alpha particle, looks like a helium nucleus, and then it leaves behind basically this atom X, but now you're also missing this alpha particle. So instead you have this atom Y, and now it has 196 for the mass because it lost 4 mass and it lost 2 protons, so it has 98 for the atomic number. Okay, next one we can look at is beta particle decay. So beta particle decay is basically a very high speed electron. Okay, that's what it is. And so essentially what happens with beta particle decay is you have a neutron and it decays into a proton plus an electron, and basically the neutron is in the nucleus, it produces this proton, the proton can stay in the nucleus, but the electron is what is ejected out of the nucleus. Okay, so that is what becomes the beta particle, and again it's just an effort for this nucleus to become more stable. And so when we do that, we can look at the equation again. So let's say we have our same atom that we started with 200 and 100. This time you produce a beta particle, and it has a mass of 0 and a charge of -1, and then it also produces whatever is left, so we'll call it Z this time, and this one has a mass of 200 because you didn't lose any mass, but it's got a proton number of 101. The atomic number is now 101. It's gained 1 because remember over here you actually produced a proton. Okay, excellent. And the last one you need to know about is gamma rays. Gamma rays we can represent like that. This is just an electromagnetic wave. It doesn't actually affect the proton number or the atomic number. So if we can do the same thing, 200, 100, and you release a gamma ray with 0 for the atomic number, 0 for the atomic mass, and as a result the thing that's left over would still be element X, 200, 100, just like that. But all of these are examples of radioactive decay. We do also need to know how penetrating and ionizing each of these are. So let's quickly go through that. So when we have an alpha particle, you have a beta particle, and you have a gamma ray. And so as you go up over here, you increase how ionizing they are. They become more ionizing, they go up. So alpha particles are the most ionizing. And as you go down, they become more penetrating. Okay. So the idea is alpha particles are really not very penetrating. Gamma rays, are the most penetrating. Okay. We can also talk about the range in air. The range in air also increases as you go downwards, okay? Right, a concept students always get confused about is half-life, so let's look at that next. So what is a half-life? Basically, half-life is the amount of time it takes for the activity to half, okay? That is really it. That is the most basic definition you can give. To give a slightly more detailed definition, essentially, if you have a bunch of radioactive nuclei, let's say you start off with 6, if you come back 10 minutes later and 3 of them have decayed, and that means you've got 3 left. That means the activity has halved, but also this is basically what half-life is. Half of the nuclei have decayed, okay? And as a result, that's what we call a half-life. And if this took 10 minutes, then that means this is equal to 1 half-life, okay? So right, T half is equal to 10 minutes. And the idea is if you come back in another 10 minutes, the amount of radioactive nuclei again will half again. So here 3, you'll be left with about 1.5 radioactive nuclei if that was possible, okay? What does that look like on a curve? Well, essentially, you might have a curve like this, which shows maybe, so you might have activity over here. You start off with a certain activity and your curve will look like this. So it's basically exponentially decreasing the activity rate, but you might have A0 over here and then half A0 over here. So you can work out half-life there. And if that was T1 and that was equal to say 10 minutes, then in another 10 minutes, T2, this would be maybe equal to 20 minutes because you've basically increased another 10 minutes, right? And the idea is over here, if you go up and you measure the activity again, you'll get A0 over 4 because the activity halved again, okay? So that's basically what a half-life is, really the most simple way I can explain it. And the important thing to note over here is you don't actually know which of these radioactive nuclei will decay. You don't know which one it is. You just know half of them will decay in 10 minutes if that is the half-life, okay? And one other thing, if you're on the higher tier, you need to know how to express this in a ratio. So you could say that at the beginning you had an activity rate of 1 or yep, and then at the end, basically that halved, right? So actually, we just flip it around. You say the current rate is 1, and at the beginning it was 2, so that would be 1 half-life. And if you was to do 2 half-lives, then the current rate would be 1, and the original rate would be 4 because it's 4 times as much. Okay, so you just need to be able to express it in ratios. You can see each time what's happening is when you compare it, it's doubling, right? Because your current rate is halving, so but that always stays as 1, so therefore you double what you started off with when you compare it as a ratio. Okay. Another thing we need to talk about is radioactive contamination and also irradiation. So first of all, what is contamination? Well, contamination is if you have a radioactive material and you bring it close to a non-radioactive material, okay? So RM and you bring it close to a non-radioactive material, just like that. That's basically all it is. Now, when you look at irradiation, it's quite similar, but there is one key difference. So with you might have a radioactive material over here. So this is basically decaying and giving off these radioactive particles. When you decay, you release the alpha particles, the beta particles, and you might bring this kind of non-radioactive material into place. And so some of that radiation can hit this, so you expose it to it. It itself does not become radioactive. Okay, so that is essentially irradiation. One other thing we want to talk about is this idea of background radiation. So background radiation is this constant low level of radiation all around us. So that's kind of the key. It's constant and it's all around us. And there's a few different sources of background radiation. So some might be from radioactive materials used in buildings or in the ground. You might also have radioactive rocks. Could have man-made sources like nuclear fallout or even the fallout when you test nuclear weapons. You could also have cosmic rays. So in space, you have these rays that go through our atmosphere or close to, and so those could also be made up of radioactive material, and that will contribute to the background radiation. You also have radon gas, okay, from rocks, which you already mentioned over there, okay? And so there's a few different things that might affect how much background radiation you're exposed to. So obviously, if you live in an area where any of these things are elevated, you might have loads of buildings or loads of radioactive material in the ground, or you live near a nuclear testing site or something like that, you'd have really high background radiation that you're exposed to. And if your job, for example, is also that you work in a nuclear power station, or you work with nuclear machines that have radioactive materials in them, then you could also be exposed to much higher levels of background radiation. So there's a few different factors that go into it. And so it's important that we actually measure how much radiation that we're exposed to. And the reason for that is the whole reason this might be dangerous is due to ionization. As we said before, these radioactive particles, they can be ionizing, right? So we said alpha particles are the most ionizing, then beta, then gamma. And what can happen is when they ionize, it can lead to mutations, okay? And these mutations can be very dangerous because they can actually result in cancer. They might also, you can also actually end up destroying different cells as well. It's quite dangerous if they're exposed to you. You can actually end up getting cancer, okay? So some precautions you might take is, if you don't obviously want to get cancer or end up with your destroying skin cells or whatever, so the precautions, you could do things like shielding. So basically you keep the radioactive material in a shielded area, in a box or something like that. You wear protective clothing, or you might use something like tongs or something like that. So these are just basic measures that you can do to, precautions that you can take to prevent that from happening. You can also monitor the levels of radiation you're exposed to. If it gets too high, you make sure that you don't expose yourself to any more radiation for a little while, okay? There are some useful things you can do with the fact that with this radiation, including with the fact that it's ionizing. So because it can destroy different cells, you can actually use it to destroy unwanted cells like tumors or things like that. You can also use the radiation to explore internal organs, okay? So the way that works is essentially you give the patient some radioactive material, that releases radiation, and you can measure that radiation at different parts of their body, okay? And of course, one thing we haven't talked about yet, you can actually use this for nuclear energy production. So let's look at that now. How do we use these radioactive particles to create energy or produce energy? Essentially what we do is we have two different methods, and one of them is called fission and the other one is called fusion. So let's look at fission for now. So fission, I'll just draw the diagram. Right, so this is what fission looks like. Essentially, you have a neutron over here, and you fire this neutron at this unstable nucleus. And because this nucleus is so unstable and it's radioactive, when you fire this nucleus into it, it can actually cause this nucleus to split apart. So you can see you produce a couple of daughter nuclei, and you also produce some other neutrons. And one byproduct of this, when it splits apart, is it produces lots of energy. Now, these neutrons that you produce, they can go on to actually create chain reactions, okay? So the neutrons themselves, remember at the start we had this neutron was fired in, so we could do the same kind of idea here. These neutrons, you line up some more radioactive or some more unstable nuclei. These neutrons hit these other unstable nuclei, and they can also cause them to split. You cause more fission, and that's what we call a chain reaction, okay? So that's how nuclear fission works. Fusion is basically the opposite of that. So before we were splitting apart, now fusion is basically where you join together, okay? So you join two lighter nuclei and you push them together. So you might have one nuclei over here, one nucleus over here, one nucleus over here. When you combine them together, you produce basically this much bigger nucleus. So this is now one big nucleus. And so what's happening here is, again, you end up producing some energy, and the reason for that is you actually lose some mass. So some of that mass that you lose when you join this together is converted to energy. Okay, so that is what happens. Right, so that is it for the whole of paper 1. If you stuck with me to this point, thank you very much. In the link below in the description, we go through this in written form. You can refer back to it really easily. There's a revision guide that you can click and find out more. And essentially, it goes into a little bit more detail as well to make sure you're completely prepped for your exam. There's a few examples in there as well. So check that out. Subscribe if you enjoyed the video, and I'll see you guys in the next one.